All right, before I start, I'd like to acknowledge my students, postdocs, and collaborators who contributed to this presentation. This year, we have observed extreme, really exceptional droughts around the world. In China, one of the most extreme droughts they observed in central China. Here in Kenya, we are in year 2 of drought, actually almost 3. In California, where I live, we are in year 3. We are entering to year 3 of consecutive drought. Europe, again, reportedly 500-year drought happening in parts of Europe. And when events like this happen, a common question is how climate change has influenced severity and intensity of droughts, how anthropogenic emissions have changed these events. So this is a very common question. We use attribution techniques to answer this question. The way it works, we run climate models with pre-industrial emissions, let's say 1850 emission levels, and then we run the same exact climate models, everything the same, but we add anthropogenic emissions. So we look at probability of, let's say, droughts, or a certain type of drought, or a specific event under historical condition with anthropogenic emissions. Let's call it P1 in this simple probability ratio equation, and the same event without anthropogenic emission, P0. And we look at this ratio, and if it is larger than 1, then basically we say that there is a signal from anthropogenic emissions in that particular event. So here we are looking at droughts around the world. As you can see, in large parts of Africa, there is a strong human signal in severity and intensity of drought. This is one example. In this paper, we show other examples, anthropogenic aerosols, and we've done other works on land use and whatnot. And this signal changes when you look at different types of events. What about temperature or hot events? The situation is even more extreme. If you look at this ratio, you see almost everywhere around the world, we have a very, very strong signal from anthropogenic emissions. These are IPCC regions. Africa stands out, of course. Let's talk about some of the processes involved in this drought and heat wave interactions. So if you have two environments, on the left, wet with lots of water, the same environment under dry drought situation on the right. So the way Earth's surface works in terms of temperature regulation is kind of how our bodies work. We lose water through the process of sweating, and that evaporation from the skin involves a cooling mechanism, and it helps temperature regulation of our bodies. Earth's surface works more or less the same. So basically, evaporation from the surface involves a kind of cooling process. And if there's drought and very little water for evaporation, the skin temperature increases, or basically the sensible heat increases in the surface. And that it can trigger heat waves or intensify heat waves. And heat waves can intensify drought because, again, they contribute to even less water availability, and that can intensify. There's this kind of intensification. So heat waves can intensify drought, drought can intensify heat wave. And these two have very strong relationship in many parts of the world. But it's not just these two. There are many other hazards that are closely related to drought and heat waves. For example, wildfires. We know that when these two happen, they create perfect situation for wildfires. And we have evidence that fires are happening at higher and higher elevations, places where later receive snow. So snow in burned environments and processes involved, we know very little about snow-fire interactions. This is one of those areas that requires a lot of basic research to see how the processes related to radiative forcing, snow-fire interaction change. There are other hazards, like rain over burned areas can create landslides or debris flow events. A big one in the news was the 2018 one in California. 23 people died in less than half an hour because of rain over burned area and debris flow. So there are many other hazards related to this compound drought and heat wave. And two or more events happen together, we call it compound event. There are many different types, many different processes involved. In a recent paper, we try to put them in different categories, different types of compound events. So like multivariate compound event is like drought and heat wave, the one I mentioned earlier. There is a relationship between the two. The relationship can be mathematically explained. So we call it multivariate compound event. But there are other types like spatially compound events when you have multiple floods and they all drain into one location, causing massive flooding, or precondition when there is, for example, rain over snow causing flooding. So snow is like precondition and warm rain on top of that. And also cascading hazards or temporally compounding events like drought, heat wave, fire, debris flow. That's an example of cascading events. So today I focus more on drought and heat wave and then some cascading impacts down the road. So I talked about attribution of droughts separately and also heat waves or warm month separately. But now let's look at compound drought and heat wave. So let's just focus on this bottom row here. So the one on the left is climate model simulations, actually many different models. You're looking at the average of many different simulations under pre-industrial emissions, so without anthropogenic. And we have basically this percent change in number of hot and dry months. And the one on the right is exactly the same thing, but including anthropogenic emissions. As you can see, the signal is very strong, more than what I showed you earlier for heat separately and drought separately. Because again, these two compounding impacts, the change or the intensification of compound drought and heat waves is stronger than drought alone and hot month or heat waves separately. And this is basically the count of events, but shows more or less the same issue. Now, the one on the left here, this figure is summarizing what I showed you earlier, average over the whole world. So the blue one is kind of like 30-year average of compound drought and hot conditions, or drought and heat wave conditions, without anthropogenic emissions. So there are ups and downs, but more or less the same. And these uncertainty bounds are basically from many different climate model simulations. But then when you look at anthropogenic emissions, again, compound drought and heat situations, you can see significant changes in the occurrence of these compound drought and heat wave situations. And remember, these two events can trigger other hazards like wildfires and other things that are happening around the world more and more. And again, the one on the right are showing basically counts of events that are summarized here in this time series. Now let's look at different regions, like for example, Mediterranean or East Africa, where we are right now. So East Africa is this one. So here we are looking at, again, separately on different regions to see how this relationship differs. Of course, the pattern is more or less the same in different parts of the world. But in some places like East Africa, for example, is one of those really extreme situations that drought and heat wave can really intensify each other. And the human signal, this is the difference between anthropogenic emissions and no anthropogenic emissions. This difference is pretty significant here in one of the most extreme, actually, around the world in East Africa. All right, so when we talk about drought, usually in 90, maybe 95% of papers, we look at geographical location of drought, like where drought is happening. What I showed you earlier up to this point was based on historical simulations, but now we are looking into future. So these are, again, from climate model simulations, but we are looking at different future conditions. These are different future climate situations. As you go further down, there are more extreme future socioeconomic pathways. So as you can see, we expect more intensification of droughts in the future. Africa, just you can see, again, it stands out, and Middle East as well. So this is a kind of typical analysis when it comes to drought. We focus on where drought is happening and to what extent it will intensify. But we know that drought events are kind of connected through food for example, trade networks, right? Food moves from one place to another, and drought in, for example, food-producing countries can significantly affect other countries, can propagate around the world. Here is an example. We developed a model that kind of tracks how food moves around the world and how events in one location can cause problems, disruptions, and whatnot in other locations. For example, if you look at, for example, 2002 drought in Canada and US, the impact in terms of food security was nothing in US and Canada. There was no change in food prices, no change in food availability in Canada and US. But the change was mainly here in these areas. So this is change in calorie supply available. So change in calorie means we look at what food actually goes from US to other countries. And if there is a deficit, we convert that to calories, whether it's corn, wheat, or everything, and we combine that together. You see that there are countries in Central Africa or also North Africa that's significantly impacted by droughts in other places. So we need to kind of bring these things together and how basically droughts in one location can affect other places and cause disruptions and social unrest. Here we are looking at Egypt and sources of food. So the yellow bar is Ukraine. This is how much food Egypt brings from Ukraine, right? This is wheat from Ukraine to one specific country. Egypt also brings food from US and other places like Canada and Australia. What if there is drought in US and war in Ukraine? How the interactions between climatic and non-climatic events change. So we have developed a model that basically tracks all these events with respect to food security. But the next step for us is to go beyond physical modeling, how changes like this can cause disruptions, riots, and things of that nature. In 2012, for example, food prices jumped significantly in Kenya because of drought in the US. Not enough to cause disruption like what happened in Syria, but still it was significant. In the 80s, it was so significant that, in fact, crime increased and all kinds of other problems. Famine in the 80s, it's very, very well known and well studied. So remember, I mentioned earlier that a drought and heat waves interact with a lot of other processes. One of them is snow. And that changes in snow can also have significant implications for food security. So if we look at here, we are looking at snow water equivalent. That's water equivalent of snow for different levels of warming based on historical data. So these distributions show changes in snow water equivalent in California. Just the differences for 1 degree plus average, minus 1 degree below average. This difference is pretty significant in terms of water availability. And we estimate that just 1 single degree temperature change will result in 20% difference in snow water equivalent. That is huge, and it can cause significant impacts. And because of that, we have developed an indicator called snow drought that specifically looks at snow separately, called snow drought index. Now, let's look at this snow deficit and implication for food security in the agriculture sector. Here we are looking at basically fraction of water used, from surface water used for irrigation in this color bar. The y-axis is the fraction coming from snow. So the hot spots are in Central Asia and Western US. Africa, you see the value is around 10%. Places of snow may not appear to be a big deal here, but Mount Kilimanjaro is headwater, and water from there drains through multiple countries. Yes, the value is probably around 10%, but that is very significant because of the sensitivity to drought and heat wave events I showed you earlier. So basically, changes in snow can significantly affect irrigation water and agriculture production. So we have, this is again the same results, but for different crops. So here we are looking at different crops around the world and to what extent change in snow can affect that particular crop. As you can see, again, for some crops and some parts of the year, that is a very significant number. The hotspots are based on our snow hazard index, which is basically a simple index that looks at deficits that you have to basically make up through some other alternative sources. Very simply, red is bad, yellow is better. I don't have time to go into the details of it. So the hotspots are, again, some places in Middle East, Central Asia, and Western US where snow deficit propagates in the system and affects like large river basins, places that they don't necessarily receive the snow directly, but snow at least propagates through drainage across multiple basins. And some of these places produce a lot of food here, and also here. And in some of these regions produce food for millions, hundreds of millions of people. And any disruption, any significant change will have global implications. So the implications will not be just local and in these basins. So we have developed models that can look into, okay, how do we translate what I showed you earlier to crop yield risk? And that's a kind of crop sensitivity index, which looks at yield relative to long-term average, standardized by basically standard deviation of all the changes we have observed in the past with different climate forcings, soil moisture, and precipitation. And here is an example for Africa for major drought years where we actually observed change in food production. And basically, this color bar shows the results of our model showing high sensitivity, less sensitivity. And you can see large parts of area falls under this high sensitive category where food production can quickly and easily change from year to year. And of course, when we talk about food security, we cannot ignore energy, otherwise Dayo would be very unhappy with me. Let's look at globally on water and energy for food production. So here I have only 2 minutes. Let's focus on this one. We're looking at water use per ton of food. So many of these countries here in Africa and Middle East, they use a lot of water for very little food. So there is a lot of inefficiency going on with respect to energy, more or less the same. So this is energy per kilowatt, basic per kilogram of food. And again, there is a lot of inefficiencies around the world. And if I summarize here, again, it's a summary of what I showed earlier. The x-axis is energy. This is the global average. The y-axis is water, again, normalized by ton of food. This is global average. And here are some countries relative to each other. This is Nigeria. The color bar shows how much food is actually being produced. This is basically a measure of efficiency. There are places that use very little water and energy relatively, but they produce very little because of inefficiencies in the ag sector, places that are more efficient, and places that are highly, highly inefficient. They use a lot of massive amounts of food and water and energy and produce very little food. This means that there are opportunities for improvement to basically address some of the issues I showed earlier. Again, most of our analysis and our literature focuses on climatic drivers. We look at drought from hydrologic perspective, meteorologic, but another important issue is what we call it anthropogenic drought, droughts that are intensified or caused by human activities. And the signal is usually drying lakes or significant environmental and ecosystem impacts. So this is one example from Lake Urmia in northwestern Iran. They started to invest in the ag sector to produce food and create jobs. So this is ag water use, and this is lake water level happening at the same time. So the ag industry improved at the cost of significant desiccation of this lake. You can even see greening in the area from satellites. And this is a saline lake. Now there is a lot of exposed lake. The situation is a lot worse right now. And dust storms are happening, sandstorms are happening. So my point here is, as we move toward improving food security issues with investments, we have to consider the environment and what is happening to it. And I think I'm out of time. Let me skip this 2 slides. With that, I stop here. I'll be happy to take any questions you may have. Thank you again for the opportunity.